Hi, welcome back. In this lecture I want to discuss the implementation with the PennyLane of one of the most famous quantum computing algorithms that takes the names from the inventor, that is Groover. So I'm going to describe the Groover's algorithm implementation using PennyLane. So what is the Groover's algorithm? Well, the main purpose of Groover's algorithms is so-called quantum search algorithm. Given a quantum state that has been marked, the algorithm allows us to detect it. So it's going to amplify the amplitude of the state, the quantum state that has been marked. So when we measure, the probability of measuring the marked state will be maximum. So this algorithm provides a quadratic improvement or a classical search. So it's order of square root of n, where n is the number of items in the unstructured database. In the worst case scenario, in the case of a classical case, in order to find an item in an unstructured database, we need to go through all the items, and therefore the complexity of this search is order n. The core idea of the Groover's algorithm is to amplify the probability amplitude of the marked state using two basic technology. One is actually the oracle that is basically a subroutine that allows us to identify the marked state and tell us if the marked state is the one. The other important quantum primitive used in this algorithm is called diffusion operator, but also it goes under the name of amplitude amplification, because it changes a difference of phase in a quantum state into a difference in the amplitude, so then we can measure them. The key building blocks of the Groover's algorithms are the following. So we first initialize the qubits in a uniform superposition, and we know how to do that. We just apply a number of Hadamard gates. We apply the oracle to mark the target state. We use the amplitude amplification or diffusion operator to amplify the marked state, and then we can repeat these steps 2 and 3 a number of times. We can show that, for instance, that if we repeat a number of square root of n, we will find the optimal amplitude amplification. So this is also called the Groover iteration. So that's something that you will find in the literature. So this can be repeated many times. But let's look at the details of the implementation. Well, the very first step is to have a device, and as usual, we do QML device, and again we use a quantum computer simulator by PennyLane, and then we use 3 qubits, so we can going through 8 items. So this is the number is quite small, so we got to have some challenging task. We should increase the number of qubits, but this is just for pedagogical purposes. We choose a number of qubits is equal to 3, and therefore we can allow to have 8 items. As the first step is very simple. We have 3 qubits, so we just apply the Hadamard gate on each wire or on each qubit. The oracle definition in this particular pedagogical implementation corresponds to mark a state. As I told you, we're going to have 3 qubits, and therefore we are going to have 8 states. Right, from state 0 to state 7. So where each of these circles represent a quantum state in the computational basis. In this case, we can use a circuit that is presented on these slides to mark the state. In this case, 1, 0, 1 that corresponds to state 5. What does it mean to mark the state? Well, what it means is that we are going to flip the phase of the quantum state by pi or 180 degrees. So for instance, after the Hadamard gate, the phase for each quantum state will be 0. We can just, if it is a circle, So what we do, we apply this quantum circuit, and if this is state 5, the circle corresponding to state 5, what it's going to do is going to flip the phase. So in this case, the phase is 180 degrees instead of being 0. What we're going to have, all the other quantum states, they have 0, and 0, 0 phase. So we're going to have this quantum state that has a flip phase. And the way to do that is to build a quantum circuit as shown in here. So you need to trust me that the effect of this quantum circuit is to flip the phase of the quantum state 5 in the computational basis. So this is the first step. The second step is to apply the amplitude, amplification or diffusion operator. That is a quantum circuit that is represented here on the slides. We apply on each qubit Hadamard gates, and then we apply NOT gates or X gate. When we apply a multi-control Z gate, and then we have the symmetric quantum circuit configuration, so a number of X gate and Hadamard gate. This can be translated in the following quantum circuit definition. This is our function, first having Hadamard and then NOT gates, and then we implement the control Z operation in this way. So this is only 3 qubit, so we're going to have the control qubit on 0 and 1, and then at the end we apply again the NOT gate here and the Hadamard gate here. When we talk about Groover's algorithm, we're talking about combining the oracle and diffusion operation in one function. So the one Groover iteration corresponds to the initialization, marking the quantum state that we are looking for, and apply the amplitude amplification. And in this case, we are determining the probability for each quantum state in the computational basis. If we try to visualize, we can use the matplotlib as we did before and visualize the probability. So the quantum state that we flipped was the number 5 or 101, that is the following, and you see the amplitude of the probability of measuring this quantum state is the highest. This is the last slide of this lecture. Talk to you soon.